The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today I'm going to start talking about diatomic molecules and this sort of thing that I've been doing ever since I was a graduate student. And I have a particularly simple view of what you need to know to become quite sophisticated in diatomic molecule problems. And I will present that. I think that my approach is probably needlessly simple, and that it would be better to lard it with 3 and 6J coefficients. But I prefer to present it in a way where you can basically derive everything yourself without recourse to tables, although that can be a very painful and laborious thing, needlessly so. Okay, so we're going to set up effective Hamiltonians for diatomic molecules. And the effective Hamiltonians basically have 2 pieces. They have the rotational Hamiltonian, which is some operator that depends on internuclear distance, and an operator, r squared, which is the nuclear rotation. These are 2 different r's. I'm sorry about that. And the other thing that you need to know about, which I love even more than this, is the spin-orbit Hamiltonian, which is, I write in a simplified form, which is some function of the individual electrons, the angular momenta of the individual electrons, and the spins of the individual electrons. And this sum over electrons is what is called a one-electron operator. And we are going to be learning how to evaluate matrix elements in a Slater determinantal basis set. And matrix elements of one-electron operators are particularly transparent. And when you have the opportunity of writing an operator in such a form, you celebrate. Because that simplifies the algebra and makes it almost equivalent to what you would have done if you didn't have Slater determinants. So these are the 2 things that we are going to become extremely skilled at dealing with matrix elements of. And the tools for this will be angular momentum matrix element, angular momentum basis functions of this form, where we have a magnitude of an angular momentum, a projection of that angular momentum into the body frame, and a projection of that angular momentum into the laboratory frame. And these are the basic building blocks. And when you deal with functions of this form, where you have a magnitude and a body projection, you don't generally care about the lab projection, although it's always there. This makes your life simple. And when you have this, you don't need to use vector coupling coefficients, because all of the matrix elements can be evaluated very simply. And so this is closely related to Hund's case A. And when you are in Hund's case A, you have the ability to write matrix elements without a great deal of thought. And that's a very useful thing. So when you're using a Hund's case A basis set. So I'm going to talk briefly about these angular momentum functions and their properties. And I'm going to give you the wigner-eckart light, because this is a tool that enables you to classify operators and simplify operators and write down without a great deal of thought a convenient operator replacement which will suffice for most purposes. This is already a replacement of the microscopic spin-orbit Hamiltonian, having used a kind of wigner-eckart light. But so anyway, these are the things that are going to be really important. In the next few lectures, I'm going to talk about, okay, how do you set up the effective Hamiltonian for a diatomic molecule? And it will mostly involve these two matrix elements of these two operators. But you will then get matrices for multiplet states which need some extra corrections due to effects from faraway states. And that's called the VanVleck transformation. It's a way of taking out of the exact full Hamiltonian the part you need to deal with as accurately as you want the little bit of state space that happens to be in your spectrum. And so there is a simplification that I'll talk about. Then I'll also talk about Hund's cases and parity and EF symmetry. So that's mostly what I'm going to be doing this week. I don't think I'll quite be able to do all of that this week, but we'll see how far we get. Okay, so first of all, we're going to deal with diatomic molecules. And since I don't want to resort to fancy tools for angular momentum coupling, I'm not going to consider nuclear spins. So the actors in this drama are the nuclear rotation, the orbital angular momentum, the spin, the total angular momentum, N and JA. So this is nuclear rotation. This is the total electronic angular momentum. This is the total electron spin. This is the total angular momentum. This is the total angular momentum exclusive of spin. In other words, it's J minus S. And JA is the atomic angular momentum. It's L and S for the individual atoms. And this you normally won't encounter except in Hund's case C. And most people don't talk about it. But anyway, those are the actors that we're going to be dealing with. Okay. So, since we're going to be talking about angular momenta, and we're going to be talking about angular momenta bras and kets, we'd like to be able not to ever look at the form of a differential operator or form of a wave function. That we're going to be dealing with this in an abstract space, and so that very much like the way we dealt with vibrational wave functions, we have an algebra that we know how to use, and we don't question it until we get into trouble because there is something that requires making an assumption that you don't know whether it's justified or not because you don't know what you're playing with. But most people, you know, when they're small children, get Tinker Toys or some sorts of models, and you build these elaborate things, you don't really ask, well, what's the nature of the plastic in that red bar? Or what are the angles? You sort of do it. And so you're going to have a kind of an idiot savant approach to diatomic molecules, which is what I do. Okay, so the way in which you deal with angular momenta is you say, I'm going to classify an operator according to its commutation rules. So these are the components of an angular momenta operator. And they can be laboratory fixed or body fixed components. And so this is the commutation rule, AI, AJ minus AJ, AI. And its value is equal to IH bar times this wonderful symbol times the other component of the angular momentum. So if you have an angular momentum, it's got 3 Cartesian components. And all 3 Cartesian components are present in this formula. This symbol is equal to +1, -1, or 0. And so if the components appear in cyclic order, so if I is x, j is y, k is z, that is +1. If they appear in any other order, then it's -1, anticyclic. And if any two indices are repeated, that symbol is 0. It's a wonderful thing, and it enables you to do very elaborate derivations because sums just vanish. You know, once you get the hang of it, it's a wonderful tool. But anyway, this is the definition of an angular momentum. And with that definition of an angular momentum, you can derive the matrix elements of an angular momentum. So you know that a squared on a basis function, a alpha m a, is going to be equal to h bar squared a plus 1 times the basis function again. So we have these things with three labels. One is the magnitude, one is the body projection, one is the lab projection. And so we'd like to know what the various operators do. And so here is now the body projection operating on the same thing. So starting with the commutation rule definition and the idea that there should be a set of functions which are simultaneously eigenfunctions of the magnitude, the body projection, and the lab projection, we can derive these matrix elements. And I will spare you that derivation because it's one of the most horrible, boring things. It's a wonderful result because you use it all the time, and you've probably seen it. But it's really quite a tedious enterprise. And so a capital Z operating in that, this gives it h bar m sub alpha, m sub a times the original function. And then the interesting stuff. You can define these sorts of operators. So I'm using capital letters for the body, and since capital letters are big, I'm putting the plus and minus up. And I forget that. I tend to use the plus and minus up for body fixed components because that's just what I fell into. But this is the way you're supposed to do it. Or I urge you to do it. Now, so we have this function, these functions which are simultaneously eigenfunctions of a squared, a little z, and a big Z. And another thing you can derive is, well, what does a plus minus do to a alpha m a? And what it does, okay, one of the rules is if you have an operator as opposed, you get an h bar for each power of the operator. Okay, but we're going to make all the h bars go away because why write them all the time? So we'll absorb them into the constants that we're going to be having. So we get an h bar and then an a plus 1 minus alpha plus or minus 1 square root a alpha plus or minus 1 m sub a. Okay, so it is possible to derive this using that definition. That is a tedious derivation, but it's possible. And you certainly don't want to see me attempt it. So when A plus or minus operates on one of these guys, you get a constant times a new function where the quantum number has been increased by 1 if it's A plus, decreased by 1 if it's A minus. That's why we call these raising and lowering operators. And you can imagine that we could write this in the form of a matrix element by just left multiplying by this guy, having this now is expressed as a matrix element. And then you'll see that you have alpha and alpha plus or minus 1, the product of the two values of alpha that will appear in the matrix element. So you never have to remember. I mean, so you can say, I've got matrix elements of this sort of thing, and I have alpha here and alpha prime here, and it's either going to be 0 or it's going to be A plus 1 minus alpha prime square root. It's just like remembering matrix elements of harmonic oscillators. There you've got a matrix element that's going to be of a coordinate if it's not 0, it's going to be the square root of the larger quantum number. Here it's AA plus 1 minus the product of the two quantum numbers. So you don't ever have to look it up. Don't ever have to look it up. And you know that this raises or lowers by 1. And that, I think, is a very useful thing to store in your memory. Better than tables of 3J coefficients. Okay, and the same sort of thing happens for A plus minus. And then instead of alpha and alpha prime, you have M sub A and M sub A prime. And so the usual angular momenta have the wonderful property that A plus, whether it's plus or plus, is a raising operator. It increases the number of quanta of the projection quantum number. Okay, so it's probably a good idea to go through a derivation of these matrix elements, assuming from that commutation rule. But you can also take it on faith. It's not an awful lot to take on faith. It happens to be true.
Does the body fixed one work the same way?
Yes. Okay, I'm about to introduce a surprise. The body fixed ones, I'm sorry, the laboratory fixed ones always work the right way. But we're about to do a little fix because the body fixed ones are in a non-inertial coordinate system, and we end up doing something that makes your life simple, but you know that it's a sin. It's something that you shouldn't do because what it is, you're doing something you don't understand why. Somebody told you to do it. But it simplifies your life, and you know, many people go through life that way. Anyway, so there's what are called anomalous commutation rules. And for body fixed angular momenta, only for body fixed angular momenta of certain types, you get a minus sign here instead of a positive sign. And what that does is it makes A plus, which is AX plus I AY, into a lowering operator. So you derive, you know, if you start with these commutation rules, you will derive a result, and you'll discover that this symbol A plus is now lowering rather than raising. And you say, I'll live with it. Now, I have tried very hard over the years to understand in a deeper way why this is true. And I can't say that I've been very successful. All right. So this is one of the dangers when we're manipulating symbols that we don't know what they mean. But as long as we're obedient and accept what someone tells us until we discover we really have to understand why it's true, we'll be fine. Okay, so we have a basis set, A alpha m sub A. And this basis set means that we call A an angular momentum that's a classifying angular momentum. So what about B, operator, some other operator? We'd like to be able to write matrix elements in this basis set of other operators. And so there is a wonderful thing, which is a baby form of the wigner-eckart theorem, which says, okay, let's classify the operator B according to its commutation rules with an operator, with a bona fide angular momentum. So what we do is we say, we'd like to know, where did I write this? Okay, we'd like to write the commutation rules of so if this is what we're going to call a vector operator, it has angular momentum like commutation rules. Although, you know, for the angular momentum, you would have an A here. So a vector has, you know, something to this. But this is how we define a vector operator. So we find an operator and we evaluate its commutation relationships with the components of an angular momentum. And we discover that it follows this rule, or this rule. That means it's a vector. We think of it as a vector.
Can't it also just commute with the...
The other possibility is we have an operator, and this operator, not the spin, we call it S because that's going to mean scalar, vector, scalar. This is 0 for all components of the classifying operator. These are the two things that you most care about. When you have higher tensorial rank operators than vectors and scalars, then you have to resort to more powerful tools. But almost everything you're going to encounter is going to be a vector or a scalar. Okay, so what's so good about a vector and a scalar? Well, if you can show that the operator in question is either a vector or a scalar, you can immediately write down a whole bunch of matrix elements in this basis set. So if you have a scalar operator, then your scalar operator operating on your basis function is going to give a number which can depend on the value of the projection quantum number. And it's not going to change anything. And it cannot depend on the values of alpha or m sub alpha, or m sub a. So it's a number that can depend on A, but can't depend on anything else. And it's a diagonal operator. It doesn't change anything. Okay, so let's begin to extract some meaning. Now suppose we have two angular momenta. Now this is the spin, and this is the orbital angular momentum. And we know that the spin operates on spin coordinates, not spatial coordinates, and L operates on spatial coordinates. And so we have a reasonably good idea that these two guys are going to commute with each other. So what that means is, well, this is an angular momentum, and this is an angular momentum, but this is a scalar with respect to that, and this is a scalar with respect to that. In other words, they operate on different functions. And so we can have spin functions and orbital angular momentum functions. And this only operates on this, and this only operates on that. And we have SI, LI equals 0. They commute. So it's a little bit counterintuitive. Here we have two angular momenta. They're angular momenta, they're vectors, whatever, but they are not angular momenta with respect to each other, and they're scalar operators with respect to each other. Okay, now another, I told you about anomalous commutation rules. Well, any operator that operates in the body frame and contains, I just want to make sure I say this right. So suppose we have J is equal to R plus L plus S. We have to be careful because with body frame matrix elements of R, L, and S, and we discover that the commutation rules with respect to the body rotation for body fixed components of certain vector operators, they're going to turn out to be, they're going to have anomalous commutation rules. And so we get anomalous commutation rules of things like L and S with respect to R, and L and S with respect to J. Okay, and now here we have a wonderful and unexpected simplification. So So what I meant to say is body fixed components of angular momenta operating with this guy are anomalous. And then what we discover is that we know that L, I, S, J, they're all equal to 0, all combinations of these guys. But what about R, I, either L or S? So L, J, that one has the anomalous commutation rules. Okay, I've got it right now. I'm on the track. Okay, so this is true for L and S. But now, what about J with L and J with S. It's going to turn out that these are going to both be 0. This is a surprise because L is inside J and S is inside J. And so you'd sort of expect, well, I'm going to get ordinary, either anomalous or regular commutation rules with these guys. But if we write this out, we write J is equal to R plus L plus S, commuting with L sub J. What's this going to be? So let's put an ion here, an ion here, and an ion here. So what we're going to get is an anomalous commutation here, which gives back L sub k with a minus sign. We'll get a normal commutation between these guys, which gives back L sub k with a positive sign. And we'll get 0 from this. So the commutation of the components of L with the components, the first two parts of big J gives two canceling terms. And as a result, we have these two commutation rules, and this enables us to write basis functions, an electronic wave function, and L lambda, a spin function, omega Jm. We can write our wave functions, or basis functions, as a product of three factors because of the fact that if these quantum numbers, if these angular momenta commute with all components of J, well then J doesn't operate on this. And J doesn't operate on this. And L doesn't operate on this, S doesn't operate on this. And so we've partitioned our basis functions into three convenient little pieces. And that's only possible in Hund's case A basis set. When you start having an angular momentum coupling scheme where you don't have the magnitude and the projection of each of the angular momenta, but instead you couple, say, J plus S, J minus S makes N, where you have three magnitudes as opposed to individual angular momenta and individual projections, then you have to use more powerful techniques. And there's nothing wrong with them, but you can do so much when you have the magnitude and the projection of every quantum number that I recommend that for establishing confidence and being able to impress your friends. Because there's no problem you can't solve in this basis set. It's just if your friends already know 3J, they can beat you. But they don't. Okay, and you can make them want to do this because you can see that they can see that there's not much there. Okay, so I just told you something really wonderful, but now I'm going to take it partially back. Because L is no damn good. We can't have L. We can have lambda, but we can't know L. But it doesn't change anything. It just means that there are certain symbols that you can't evaluate. You have to manipulate them as symbols. And you let the molecule evaluate them. But it doesn't cost you anything in terms of the rigor of the manipulations you're going to do. So why is this? So we have an atom here, and it sees a spherical world. And if there's spherical symmetry, L is good. Now, we have another atom here. Goodbye spherical symmetry. So we can think about this. You still have cylindrical symmetry. So you can think about this as saying this atom interacts with the electrons in this atom by applying an electric field. which is axially symmetric. And so the electric field will pull electrons, say, this way. And it's just like the Stark effect. And the Stark effect is, the Stark effect you can describe as a vector operator. And the vector operator has the properties of mixing L with L plus or minus 1. So you have, and it's the Z component, because this is the cylindrical symmetry. So M sub L, so if you apply an electric field to an atom, you mix L's, and you know that because atoms have electric dipole transitions where L changes by 1. But M sub L doesn't change. So this simple argument says, okay, in a non-spherical world where you have molecules, diatomic molecules, L is not going to be defined either for the individual atoms or for the molecule. But the projection of L on the body frame is preserved. This is a little bit counterintuitive because you're destroying the thing that gave rise to the projection, but you destroy it in such a way that the projection is conserved. Not a big deal. So how much time do we have? Oh, we got plenty of time. So we have a basis set where we normally don't write L in here. And that's the electronic wave function. And this N is a symbol for anything you might choose to know about the electronic wave function, like its electronic configuration. And then we have S sigma. And we're entitled to say something about the body projection, the lab projection of S, M sub S. But we normally don't worry about that unless we're going to apply a field that interacts with the electron spin. That would be the Zeeman effect. And so, but if we understand the Stark effect, or if we understand the interaction of radiation with the orbital part of the wave function, then there's nothing mysterious here. We could deal with that. But, so we tend to not include quantum numbers we don't need. But if we need them for the particular term in the interaction, we'll pull them out. So we have J omega M. J. So these are the three things, and these are our friends because we know what L plus and LZ do to this. We know what S plus minus and SZ and S squared do to this. We know what J squared, JZ, J plus minus do to this. And so there's no matrix element of terms in the Hamiltonian that we can't evaluate. So this should be pretty exciting because you can see that there's an awful lot of problems that you can solve without thinking about it anymore. So I forgot, there's one more, the vibrational wave function. And that, remember, the vibrational wave function is kind of dependent on J, but that's something that we deal with later. Okay. So, to prove that we can actually do useful stuff, let's start working out the matrix elements of the rotational Hamiltonian. That's half the problem. For diatomic molecules, really, all there is spin orbit and rotation, and so we're going to do rotation. Okay, so the rotational Hamiltonian is B of R squared. And so this is a scalar operator. It operates only on the vibrational wave function. And so we have Okay, now because this is a function of r, you know that from your homework on Herman Wallace and other things and centrifugals. So we can have two indices here. But we normally only have one. We normally are only interested in diagonal matrix elements of the rotational, or matrix elements of the rotational operator within an electronic state. But it's sometimes possible to have matrix elements of the rotational operator between what we call different electronic states. But what we call different electronic states is partly partly based on our approach. What have we, what are we grouping together arbitrarily, and what are we, and that comes from this. Okay, so we have this part, and we can sort of forget about it. It's just going to be a constant, either b of v or b of v prime, depending on what we're dealing with. And now we care about that. And so we have r is equal to j minus l minus s, because this is the nuclear rotation. J is everything. So j is r plus l plus s. And but it turns out we don't want j. And so we have j minus l minus s. We want r squared. So we square this. And now one could proceed without further insight. But here's a diatomic molecule. And the body rotation, the rotational angular momentum is necessarily perpendicular to the body axis. This is not true in nonlinear polyatomic molecules, and so maybe it's a bad habit to exploit this simplification. But since r is necessarily perpendicular to the body axis, we can write this as rx squared plus ry squared, which is the same thing as jx minus lx minus sx squared plus jy minus ly minus sy squared. Less algebra, much less algebra here. Remember, these are three components, and there are commutation rules that you might have to worry about, although I told you that the components of L and S commute with the components of J, surprisingly, unexpectedly, better than you deserve. So it turns out that you don't have commutation problems. But anyway, this is how you can write these things. And so then you just start doing the algebra. And you're going to get a jx squared and a jy squared. And there are a lot of similarities to the way you handle a polyatomic molecule asymmetric top. Because even though you'll see. And you'll have an lx squared plus ly squared. And sx squared, sy squared. Well, what's this? This is j squared minus jz squared. And that should make you feel warm all over, because j squared and jz are operators that we know the matrix elements of. And this is s squared minus sz squared. So two pieces. Now, this is L squared minus LZ squared, but we don't know L. L is ill-defined. So we call this J squared minus JZ squared. We call this L perpendicular squared. And we call this S squared minus Z squared. So now there are cross terms in here. And I haven't dealt with the cross terms yet. But I'm just pulling out the nice ones. And so, so we're happy about this, and we'll deal with that. And what we do is we say, well, L perpendicular, we don't know what it is. It's a number. It's a small number, and it multiplies B, and we'll call it a contribution to the electronic energy. We'll lump it in with the electronic plus vibrational energy and forget about it. That's what people do. It does result in a small isotopic contribution, which, if you forget about it, eventually Mr. Ogilvy will tell you you've made a mistake. And none of you ever want to meet Mr. Ogilvy. But if you go to the Columbus meeting, you probably will actually see him making a fool of himself. Okay, so we have some cross terms too. And so we're going to have cross terms that have the form 2, jx lx plus jy ly, and minus 2 jx s x plus jy sy plus 2 lx sx plus ly sy. Okay, so those are, there's a beat. So these are what's left over. I guess I didn't multiply. Let's forget the b's for now. Okay, so what do we do with these? Well, you can show that this is the same thing as j plus L minus plus j minus L plus. And this is the same thing as j plus S minus plus j minus S plus. J plus is a lowering operator. L minus is a lowering operator. J operates on the part that gives you omega. This operates on the part that gives you lambda. And so the fact that omega is lambda plus sigma, you get no problems. This changes omega in just the way it has to in order to keep up with this changing lambda. It's very easy to get confused by this. So both of these are changing the same corresponding things in the two pieces of the wave function in the same direction. Okay, and this one is L plus S minus plus L minus S plus. This is called L uncoupling. This is called S uncoupling. And this is just called rotation spin, or spin, rotation electronic interaction. Okay. This doesn't have a name because it's never big. These two have names because the matrix elements of these are proportional to J, and they get big. And you can never ignore them. This is always, this can be 100. This is going to be 2. And so you do have to keep track of it, but it's not so important. And so one tends to ignore it. And also, it's going to have the same form as spin orbit. And so you'll lump it in with spin orbit and forget about it. So these two things, it's called L uncoupling. And L uncoupling has the property of destroying lambda. S uncoupling has the property of destroying sigma. Both of these have the property of destroying omega, because omega is lambda plus sigma. This one doesn't destroy omega. Doesn't do much. It does spoil both lambda and sigma. Okay, so now we have reduced the rotational Hamiltonian into convenient form for writing down all the matrix elements. And I think this is just the most amazing and wonderful thing. And the only problem with it is that we cannot do much with a symbol like that. We know that this symbol is going to give rise to n prime lambda plus 1. That we know. But we don't know values of matrix elements. So what we do is whenever we have a matrix element involving L plus or L minus, we define a symbol, alpha or beta. That symbol represents a matrix element, either a spin orbit or a rotational matrix element of L plus. And we will manipulate those symbols honestly, but we don't know the value of those symbols unless we do a quantum chemical calculation, or we allow the molecule to evaluate it for us by giving us something in the spectrum that determines the magnitude of this matrix element of L plus or L minus. So we're almost done. We tend to think of, well, we tend to call an electronic state by the symbol 2s plus 1 lambda. We call this a multiplet state. So this is a state that has a definite value of lambda, a definite value of the spin. And so if the spin is other than 0, there will be several values of omega and several values of sigma. And so this is a multiplet state, and the different components of the multiplet state are split by spin orbit. And so because spin orbit is small at the beginning of the periodic table, we think of this as the normal building block for electronic structure. We say this is a state. We say we have a triplet pi state. The triplet pi state has lambda of 1 and sigma 0, plus 1, or minus 1. And so we can have omega equals 2, omega equals 1, omega equals 0. And it turns out you can have plus and minus parity for both. And so this is really 6 electronic states. But we call it 1 electronic state. And so the term S uncoupling operates within a multiplet state. And it just leads to complexity in the spectrum of an isolated state, because it's really 6 states or a bunch of states. And L uncoupling operates between states, because lambda states are relatively far apart. And so it's normal to think of them as separate, but the L uncoupling term can mix states of different lambda. And these are called perturbations, because you can normally ignore them unless states of different lambdas are near each other, and then something happens. And so S uncoupling happens within an electronic state. We've called the electronic state a multiplet state. And God didn't tell us about multiplet states. It just happens that spin orbit is usually small at the beginning of the periodic table, and that's where we learned about spectroscopy. So, and then we have these other terms that cause trouble. But now S uncoupling is what's responsible for going from case A to case B. It's the thing that destroys lambda. By destroying lambda, you get back capital N. So you lose one quantum number, you get another one. And so the most universal problem you experience in spectroscopy is the fact that as the molecule rotates, the spin orbit splittings, which I haven't talked about, get overpowered by the S uncoupling, and you go over to Hund's case B, and that leads to a different characteristic pattern than the spectrum. But it doesn't matter, you can still describe any limited case in case A. And so all of the empowering things I told you about today, Hund's case A, you can use regardless of what the molecule is thinking, because you're smarter than the molecule. You've got a tool that can capture whatever the molecule can do. And so it can go over to a different level pattern, but you'll be able to describe the pattern with your case A Hamiltonian and case A ideas for where do the intensities come from. And so this is enough to really do a lot of really powerful things. So on Wednesday and Thursday, I will go deeper into these multiplet state effective Hamiltonians. And I think by the end of the week, you will know about diatomic molecule electronic spectroscopy about as much as I was able to learn in my 6 years as a graduate student. But you know, a lot of this is false. You know, you go down, you think you understand, and then you discover that that's not necessary. So this is a distillation, but I think it's a very useful distillation. Sir?
So if we look at molecules deep into the periodic table,
Yes.
where spin orbits are important.
Yes.
So, I don't know, xenon dimers, for example, should we never think about something like the standard multiplet state for something with a deep spin orbit?
Well, you certainly are not going to think about it in case A, but I can still show you how to evaluate all the matrix elements for a xenon dimer. But what I would do, and depending on how much time we have and what choices we make, I will write a separated atom basis set, which is, you know, then I can do a case A-like treatment for each of the atoms, and I can build up the molecular states out of separated atom states. So what I like to do when I approach a spectrum is I like to break the thing down into pieces that I can kill, that I can represent simply, and then I bring the pieces together. And usually that's not too hard if there are a small enough number of pieces. And so that'll be the attitude I'll be taking when we approach spectroscopic problems throughout the remaining lectures in this course. Okay.